results. Okay. So this is work that was done recently and is underway with people at Penn State. And there's a list of names in chronological order. And my name would be way over there. Some graduate students, postdocs, and then Deirdre Shoemaker and Pablo Laguna, who were at Texas, so it's a sort of Texas collaboration, and myself. We had a paper that came out 3 weeks ago now. It's on the archive, and it's about the subject of this talk with a slightly less flamboyant title. So what I'm going to do is turn this. So let me just give you a quick technical picture of what we're going to do. We've done a number of simulations of non-spinning black holes. The simulations set up data with two equal mass black holes separated by a fixed amount, which is 10 times the total mass of the system in the coordinate system that we use. I'll try to explain these technicalities in a minute. And we consider a series of orbits. Here's an example. What we do is we start the black holes off at an angle which is 26 degrees from head-on. 26 degrees happens to have an arctangent of a half, so it isn't exactly 26. Now, you can imagine that these things came from way out here, and so as they came in, and this is the result of the conversation just a few minutes ago with Mike and Latham, as they come in, their angular momentum stays roughly constant, although you can see that there is some curvature right after we start the orbit. But then they do something like this. They're mostly head-on. This one does about half an orbit before it merges. Okay. The data that I'm talking about, was the results I'm talking about are based on about I think it's 33 simulations like this that were done at Texas. And we've looked at a number of different configurations like this. Now, every one of them has the same separation and the same angle, but what we did was just increase the momentum of the initial data set. So that's like shooting them in from infinity with that impact parameter, which the impact parameter is about 4.5 m. I say about because we only set it at 10 m, not at infinity, so it's about that. Anyways, we increase their energy. We just look at the orbits. And these are roughly head-on, but as you can imagine, if you try hard, you can make them shoot past one another. And all of the orbits that we consider, incidentally, are unbound, meaning the total energy in the system is greater than the bare masses of the black holes, the individual masses of the black holes at the beginning. I've got a list of 6 cases here which I'm going to talk about, and they're just typical cases in this set of 30-something that I wanted to show you. And I've parameterized them 2 ways. One way is to parameterize them by the initial angular momentum of the orbit divided by the initial mass. In relativity, angular momentum is mass times velocity times radius. And I'm using relativist units where distances are measured in mass or mass is measured in distances. So angular momentum and velocity is dimensionless. Angular momentum has a dimension of square of the mass. And I just plot these cases. These are the same cases, but they're just parameterized by 2 different schemes. This is the initial angular momentum divided by the initial total mass, and this is the initial angular momentum divided by the mass of the final black hole. And you might say, well, why bother? But we'll see in a minute why it makes a difference. And those, as I said, are just 6 cases. This one is the first one here, so you can see it's not terrifically interesting. Now, as Latham said, there have been some recent breakthroughs in computational black hole interactions. The first good results were by Franz Pretorius, who uses a scheme which is explicitly hyperbolic. So this is a formal statement about how he sets up the Einstein equations. And he also in almost all cases, uses initial data that is constructed by actually collapsing something. So France sets up non-spinning black holes, which are made by collapsing a field of scalar radiation, and evolves them by an explicit second-order method where practically everything solves a nonlinear wave equation. Now, the Einstein equations are nonlinear wave equations, but the formal way that we do it, that we actually handle the evolution, is usually not to explicitly solve wave equations. So I'm quoting a couple of papers here. Those were his first papers where he presented these results, and it was really quite a breakthrough because we have been working on merging black hole simulations for a long time. There was something called the Binary Black Hole Grand Challenge, which started in 1993, 15 years ago, and that had a collaboration, a serious collaboration of 7 universities and finally 8 universities that worked basically full-time on it, something like 40 people seriously working on the problem. And and it took us another 10 years to get to this point. Other 2 papers that I want to mention is this other method of doing it. The other method is called the puncture method. And it's named after a way of setting up initial data. In the Einstein equations, you have to solve the initial data first. It basically means that you have to make your initial configuration consistent with a sort of nonlinear version of Newtonian gravity. So you actually measure the weight of waves that happen to be in the system. And then you evolve that once you've got a consistent set of data. The puncture method is a way to solve that initial elliptic problem. And it was around for at least 10 years before people started trying to use it for evolutions. And Campanelli and her collaborators and Baker and his collaborators announced these results at the same conference in 2006. Then they both came in and told me that they had some exciting news, and they wouldn't tell me what it was. And then they each gave a talk which said basically the same thing. You can figure out how to allow the punctures, which are singular regions in the space-time, to move through a grid. As long as they never actually hit a grid point, you can handle their singularities, and you can evolve orbiting black holes and, in fact, involve them to a merger. And that's the method that these results that I'm describing are done with. That's the method we used. And so this is a multimedia talk, and so I just want to point to the blackboard because I didn't get all these slides finished, and that's not really my computer. A couple of papers by Herman et al., and actually it's the same list of authors except in a different order as the one we saw on the title page. In 2007, we did a number of examples of the interaction of spinning black holes, and in one case we did quasi-circular, initially almost circular orbits, merging black holes with opposite spins, and we found astrophysically interesting kicks. We got kicks close to 500 kilometers a second. And so this would suggest that if you merge a couple of black holes in the middle of a galaxy, there's a fair chance you'll knock the final black hole out of a not too heavy galaxy. There was then almost immediately a paper by the Campanelli-Luosto group that showed that there was a different configuration that gave much bigger kicks on the order of a couple thousand kilometers a second. So that would knock them out of any galaxy, and that would be very interesting from the point of view of doing astrophysics with black holes involved, particularly in the middle black holes that have merged in massive galaxy mergers. Now, okay, that's great. The group at Penn State and I have been thinking about a different problem, and since the technology has gotten good enough so that we can actually do it, we were drawn to a recent paper by Pretorius and Khurana. Pretorius and Khurana did the following. They said, suppose I take two black holes that are separated by some distance roughly comparable to our distance, and I give them some velocity transverse, okay? Now, if I give them enough velocity transverse, they're in a circular orbit. If I give them less than that, they fall in, and it looks more or less like the orbit I showed you. Now, what they did was to find the parameters that have the orbits come in and spiral around a long time before they merge, and then you nudge it just a little bit, and it'll spiral around and go away again. And if you give a little less transverse momentum to the system, it'll come in and it'll orbit not quite so long. So they found that there's actually an exponential dependence on the initial momentum that tells you how many times you orbit. And there's a threshold at which you orbit a number of times, but then you fly away. And so they found this bifurcation in behavior. So the collaboration that I named decided we'd go redo that and just see whether we agreed and see what the results that were that we would get. And that's what I'm talking about today. It started out as a theoretical question about how do these black holes behave if you have these critically tuned mergers, which is an extremely interesting question, and I'm going to address it. But along the way, we found something that looks to be really astrophysically interesting, too. So it proves that you should never be too skeptical of analytical work. OK, so let me see what's on the next slide. OK, so this is the technical stuff. First of all, I have to compute this somehow, and I'm going to compute it using the puncture method, which starts out with a conformally flat space-time. That means that there's a background flat 3 space that you can use for coordinates. And then you put something which looks like m over r. It modifies the metric. Just like in Newtonian physics, that's your solution. The remarkable thing is, contrary to my expectation, you can actually evolve these things around the grid so that you can do evolution using this puncture method. And you actually have these m over r singularities rattling around in the grid. As long as they don't actually hit a grid point where you have to evaluate 1 over 0, the techniques that were worked out first by the groups at Brownville and at Goddard, the Campanelli and the Centrala groups, Baker and Centrala, they work. And finally, we're using the standard code, which is cactus and carpet, which are parallelization and adaptive refinement. No. If you start them off a grid point, they'll never hit one. Unless you measure 0. Unless you have a high symmetry, they won't hit.
Presumably, though, if they're not close enough to a grid point, numerical limits would suddenly be
Strangely enough, that has never arisen. Now, you're certainly right, Ethan, but they have to be very close. And I mean, actually, the first examples, they were non-spinning and equal mass, so they would stay in a plane, and people actually made sure that they were moving along halfway between. But it turned out later that you could relax that, and they come rather close. But you have a dynamic range of 10 to, you can do 10 to the 8th at least, so you have to get pretty close. Cross-section for that is small. The computational parameters that we do, as I said, their initial separation is 10m. The rest of this stuff is technical about the computational setup. It has 10 refinement levels. The finest refinement level has a finite difference grid spacing of total mass divided by 45, which is finer than has been found to be necessary to make these things have convergent waveforms. And if you listen to me talk as if I'm talking about weapons of mass destruction related materials, it's because they don't converge. Those punctures are singular, and so they don't converge very close to the puncture. However, this makes them converge well inside the apparent horizon of a single black hole. And it also makes the waveforms from the evolutions converge. So this is considered, and I believe it, good enough for government work. It's good enough to make sure that we're getting reasonably accurate results. We then have 10 levels. The coarsest one is like 10m, which is quite coarse. The finest 6 are adaptive, meaning they follow the black holes around. And then the last 4 are fixed, just refinements as you go out. We also extract the radius at 30M, or in most cases 50M. 30M is as close as we get. And a lot of the figures, well, I'll tell you which one it is. And on that scale, the resolution is about 1.5 M. The wavelength of this radiation is about 20 M. So we've got about, the discretization is about 1/20th of the way. So what I'm going to do is to show you those 6 orbits, and you might say, well, which 6 were they? But I'll remind you at the bottom of the page as we go along. And this is a set of orbits, each of which is unbound, as I said, and I'm just going to repeatedly increase the momentum that goes into the orbit and show you the result. So this is that almost head-on orbit, the first one, the one I showed you very first, and it has a reasonably small momentum here, so it's basically spirals in, and if you get up close, you can see it's about half a orbit. And it produces a waveform, and from our knowledge of what has happened before, what's gone before, we can understand this waveform. First of all, this is junk. It comes from the data setting method, because the data setting method makes some mathematical assumptions about the fields, which have one effect of putting a little garbage radiation in the field. And the fact that it's high frequency is a good indication that it's garbage, because there's no part of that dynamics that should produce a high frequency. So once we get to about here, we start to believe the waveform, and it goes up and then it comes down again. The part before the peak is usually considered to be the merger. The only way to really tell if there's a merger is to look for horizons in these data, and we haven't done it yet. Sorry. But other experience says that the highest peak, which would probably be this one, usually occurs right at the time that the central black hole forms. And this is surely what you expect from a formed black hole. This is a ring down like a bell. And we can check the frequencies and decay rates, and we get reasonable comparisons to what we compute in terms of the fields, in terms of the radiation of energy or angular momentum. The masses and spins come out reasonably close, although the ring down match is rough. It's usually on the order of 20%. So I'm just cranking up the initial momentum here. And in this case, I get one that does a whole orbit before they merge as they spiral in. And I still have my garbage, but it looks smaller because the whole amplitude is bigger. I have my peak, and then I have my ring down, and because the whole amplitude is bigger, I can actually follow the ring down for a longer time. It's a very pretty picture of what happens when you merge black holes and stir up the remaining black hole. This one is quite interesting. This one has an orbit which comes in, does some orbits. People were asking me earlier how many, and I actually don't know, and then merges. So it comes in, does a number of circular orbits, and then merges. Here's our junk, here's our peak, but look, it sort of flattens out and then it decays. So this is probably where the merger forms, and we get this ring down. This is from these multiple orbits. Now, what's going on here? Let me explicate it just a little bit. The plot on the left is how far apart are the black holes. So they come together and they stop moving together, and they hang there for a while, for about 60 M, and that corresponds to the about 60 M, which is this shoulder. Notice, let's see, this peak is bigger than this one. In fact, this one is bigger than that one, and these two are about the same size. So they are not, it's not decaying away. It's actually hanging there at this constant radius. And the radius is 2m total, but that is, and that sounds like the surface of the black hole, but this is a different coordinate system. So the black hole has probably not formed until later, somewhere about here perhaps.
It looks like there's a time delay between those two graphs? Is that just
Yes, the
propagation delay?
extraction radius for this one is at 30, so you just have to wait for it to get out. The next, in keeping with the fact that this is a multi-medium presentation, I think I have a movie of this. If I can, yes. Question is, can I? Okay. Okay, here we go. Top one is the orbit. So watch it. It sort of loops around and does a breather and then merges. Yeah. I think it's about 2 in this case. I'll show it one more time. Oops. Okay, that's all the animation I had. Okay, so that's an example of something which is similar to what Franz was talking about. That is an orbit that comes in and spirals for not very long, but for a while, and then merges. Now, so I've shown you 3. Let me show you another one. This is a rather interesting merger, and I wish I had a movie of it, but I don't. So we have an orbit that comes in like this, goes out here, and then comes back in, and then you get a short circular orbit, and then you get a merger. So what we have here is a waveform, of course, that has a signal from the first pass, and then it has a signal from the merger. And the signal from the first pass has this interesting look. It's very symmetrical. The signal from the merger, it looks like a merger. There's something at the beginning, but then it rings down like this. So in the first pass, what we have is they fly by like that, and it's like a Bremsstrahlung encounter. And actually, this waveform, if you do the Fourier analysis to get its frequency dependence, is like was done in a paper that Javas Nutko and I did in 1974, where we analytically computed this Bremsstrahlung radiation. Yes.
Do you know what the speed is during the circular part? I mean, how close to speed?
I don't know, but I can find out. So we're very pleased actually just to see that. This has also been seen in some other simulations whose authors I've forgotten, who are intentionally doing high-speed flybys. So this is an example of a case that has quite a complicated behavior. Oh, in fact, I've got the separation here. So it comes in from 10 am, goes down to 2 in these coordinates, back up to 14, and then merges. So it's not surprising that we get 2 bursts with relative silence in the middle, because if it's 14 am, there's not much radiation. There's some, but not much. Why is the amplitude getting?
This in comparison to the other case that you showed?
The amplitude on these graphs is arbitrary. And I don't have a good feel for that. However, I'll show you the emitted radiation, which for the most part has just been going up. So the amplitudes have been getting bigger, but the scales on there are not. They don't mean anything. Here's another one. This one does a similar thing, except it actually goes out further. And again, we have 2 radiation bursts. This is extracted at 50 M, and the reason is that the orbit actually goes out to about 25 M. So it's the same sort of thing. It goes up, comes back down again. I'd like to show you that there's a little bit of shoulder here. So again, as it's coming in, it sort of hangs up a little bit. And you can tell if you look at this that actually the first part of this wave has a lower frequency than it has in, say, the previous case. So there's something like a hang-up that's happening there that sort of lowers if you're at a larger radius, you'll have a lower frequency radiated system of radiation. And then finally, and this is the last one that I have, this orbit comes in, goes close, goes out, comes in, and breathes, and then merges. And there's the plot of the distance. That one goes out to about 30. So we have a first minimum, which is the flyby. We have another minimum, which gives us this longer radiation precursor here, which might be a third pulse. And then we have the merger, which actually has a ring down on the end of it. So this is like skipping a stone. We come in, bang, we lost some energy doing that. We skip in, maybe if we've tuned conditions right, we can make it skip again. And this result is as close as we have gotten, because once we started seeing these results, we adjusted our sights. It's as close as we've gotten to Pretorius and Corana's results. In fact, we have not seen an orbit that does a whole lot of orbits at constant radius, which is what they found. On the other hand, we've seen things that look like they're flyby orbits, suggesting that maybe if they had extended their, or maybe they've done it and just didn't publish it, if they extend their evolution long enough, they would see this kind of behavior. So we have really remarkable dynamics in these things, and it suggests you could do multiple skips. Because it's very lossy, it would take incredibly critical tuning to get a large number of multiple skips. But it looks as if we could have 3, or maybe if we got very lucky, 4. I should back up and mention a bit of astrophysics, which is that although in binary black hole mergers, one typically considers the fact that radiation will slowly circularize the orbit, and so that you're talking about quasi-circular orbits as you come in. That may or may not be the case in globular clusters where you might have multiple black holes that interact in a 3-body way and give you eccentric orbits as a result, or in supermassive interactions in the middle of galaxies. So the behavior of these orbits is interesting, and we are hoping to use these things as input to some studies of the behavior of black holes in globular clusters. Okay, so those are the orbits that I want to describe. Now, as I told you, we have looked at the radiated energy, and it goes up to a little over 10%. There are 33 points on here. This is the radiated energy, and it goes up, as I said, to a little over 10%. These jiggly points here are those funny orbits. And there are 2 possibilities here. One of them is that this is numerical error because they're weird. I should say that if we were to take that last orbit I showed you and add 0.1% to the initial momentum, we would get something that just looked like a flyby. Actually, it would do a loop and fly by. So it seems to really be unbound at that point. On the other hand, this kind of loop in some sort of parameter space diagram is often the indication of some kind of unstable behavior. And so it may be that it's real, and we're just under-resolving that sort of loop. We don't know, but it's of great interest to try to find out. What time is it? the other thing is that, as I told you, the system is unbound. It has a lot of energy compared to the bare mass of the initial black holes that we start with. So what one does is to compute the horizon area of each of the black holes at the beginning. And that's taken to be their mass, their bare mass. You then add that up. But to that, you have to add kinetic energy. And so you get something called the ADM mass, which is actually the mass you would measure if you were orbiting the system very far away. It determines that motion, that behavior. And so this is a plot of the radiated energy versus ADM mass, and obviously it's got an inverse looking plot, which is the final mass of the black hole. So the final masses of the black hole go down and decrease by a little more than 10% in the maximum case that we have. This is not to say it couldn't be more, but even these funny cases are lying very close to this curve. And these are the ones that are sort of the cutoff, the limit of this process. If you have things very far away and they shoot past, they won't radiate any gravitational radiation. They won't radiate any energy. So the title of this talk had the word teleology in it. And this is a graph which shows what I'm talking about. The bottom curve is the amount of angular momentum that's radiated in the orbit as a function of the initial angular momentum of the orbit. But it's the initial angular momentum over the mass of the final black hole squared. This is the radiated amount. This is the final amount. The final amount of the total angular momentum in the final black hole divided by the mass of the black hole squared. So that's a number. It's a pure number. And the maximal value that that pure number can have for a Kerr spinning black hole is 1. And so you see that it's 0.8. Or it's 0.78 actually at the maximum. So we found that there is an upper limit to how fast you can spin up the final black hole by orbiting and colliding to initially non-spinning black holes with the particular set of parameters that we are using. And you might say, okay, that's interesting. Maybe that maximum would be different if you tried some other data setup. We were just doing a one-parameter search, and that may indeed be true. There are two arguments that I make to suggest that this is a general result. One of them is that we were just setting up these things with a given angular momentum and a given energy, and that's like setting up the impact parameter from infinity. So, plus the energy. So it doesn't really matter, for instance, if we went in closer when we set them up or if we went further away. And I intuitively, although I don't have a good mathematical reason for this, would say that our case, which is like this, we set them up like this. They make an angle to the line between them, and we get our angular momentum like that, is likely to be very similar to the Pretorius case, which is like that, where he gives them an angular momentum that is, a kick, a velocity that is actually at right angles to the separation between them. So one thing that we intend to do immediately is to be in communication with Franz and see whether, A, he's done further examples, whether he looked at the final momentum, angular momentum, for instance. So that's a kind of qualitative reason why I think this is general. A more teleological reason that I think this is general is that if I look at the value of input angular momentum that gives me the maximum, the number is 1. So if I put in enough angular momentum into the system, into the orbit, so that if I just create the black hole, which has that final mass it will have, and put all that angular momentum into that black hole, I will get a maximally spinning black hole. It can't spin any faster. Okay, that's this point right here on this axis, L over mh squared equals 1. That is, in fact, the value of the input angular momentum that gives exactly the value that gives me the maximum final spin for that black hole. So there's something teleological, something really interesting going on to get from here to here. Now, this could be an accident, although those numbers are accurate to 3 digits when we do the computation. And I will argue that the first 2 at least are sound. It is computation, so, you know, I'm not going to bet $1 million on it, but I bet 100,000. The accident, which it may be, would have to be remarkable if we had picked just exactly the right angle so that it came out to be 1, as opposed to Franz, who picked a different angle, and I bet, although I don't know, will show that it's 1 also. Now, I mentioned a couple of papers when I began. I wrote them up here by Hermann and al. And those are papers about spins of black holes on circular orbits and the kicks that are the result. And there's been a lot of analysis by a group of people here at CITA, including a lot of work on one of the papers that we wrote, which had differently aligned spins and how they affect the kick. In fact, there's a long paper by Boyle and Kesden which has used quite a few of our simulations and gotten extremely good fits to our simulations by a method of expanding the answer in terms of the spin components and powers thereof, and matching a few parameters to pin down what the coefficients are. So I say teleology, something is going on. Some great mechanism in the sky is taking us from a maximal value of the angular momentum to the maximum value of the angular momentum. And I have been talking to Boyle and Kesden this morning, and so maybe it's just symmetry. Whoops, there's a Y. Okay. That's what I have. Thank you very much. Yeah.
Just something on the simulation for those of us who don't do this for a living now. Obviously, at some point, you had to check whether or not you have input black holes, if they are really black holes, if they have horizons or
Yeah.
whatnot. And I suppose the easiest way to do that would be to look at the gravitational wave leakage. So you know you have stuff going on inside where that horizon is numerically, whether or not that produces gravitational waves outside where the horizon should be, or equivalently, you send a gravitational wave in, you see reflections.
Well, those questions are not, I mean, they're good questions and they're not necessarily easy to answer. But one thing that I can answer is this. We are aware of the fact that there's some leading junk on all the waveforms, which on physical grounds you wouldn't expect to be there. I mean, after all, that's when the orbit is at its quietest. So we know that there are some errors made in the initial data. What you're asking there is a question about the initial data. We also can do a test where we move them farther apart and find that things like that go down. So we know that it's caused by the initial data solution, the overlap. In terms of, for instance, reflecting waves off of black holes, that's a subject of its own. These modern nonlinear codes have not been used to address that yet, although people, including myself, have done it for linear waves on black holes and seen expected results, and actually some kinds of not quite so expected results. Things that haven't been interpreted this way but actually consist of a wave hitting a black hole and starting a ring, an oscillation that runs around the black hole and beams radiation in a given direction. If you look at that in terms of scattering cross-section, it just means that you see a peak in the scattering cross-section in some direction. So We're reasonably confident based on the idea that we've done convergence, and convergence leads to similar waveforms. However, we do have a specified method of setting initial data, and that is guaranteed to put some arbitrary and, well, it's not arbitrary, but it's uncontrolled radiation in the initial data. And so you simply have to say, I can't believe that. I can't believe that first burst. If you can set up something, if I could set them up even further away, as it started, that first burst would be very weak, and then it would only be when they got rather close together you would see this main thing, and so it would be less important. It's always a problem. The other thing is that if you set them up very far away, it would be weak and it would go away because it consists of radiation leaving the system. So then you could start looking at the waveform later and still get the whole waveform. So you're pointing out a short time deficiency in these things. But part of the reason for that is we're putting them relatively close together, has been pointed out to me several times today.
So if you consider spinning black holes, you merge spinning black holes inside spins, so the conjecture is that you'll get the maximum dimensionless final spin parameter when the sum of the initial spins and the orbital angular momentum is equal to the mass squared of the final black hole.
That's a conjecture, yeah. We're trying to find that out, right, yeah.
For arbitrary initial spins, we get the maximum final spin when the total angular momentum of the system equals divided by the final mass squared is unity. That's, I guess, what...
That's a pretty powerful conjecture.
Yeah, that would be...
I don't know.
Yeah.
For people who don't know, if you take two spins and just merge them together, each of which is extreme, because of the fact that it's angular momentum divided by m squared, you get a half. So if I took two spins in one of these orbits and pointed them out parallel to the orbital angular momentum, that would add a half to the number I got, which is 0.8. So that can't happen because that amounts to more than 1, which is the maximum for a spinning black hole. So something has to happen to radiate away that angular momentum. In terms of this maximum that we got, 0.78, that was done with two equal mass black holes. But there was early observations in the paper by Bardeen and Thorne, papers by Bardeen and Thorne back in the 70s, that if you just take little particles and orbit them in, they don't radiate away very much angular momentum, and they will deposit their angular momentum in the black hole mostly. So you can spin a black hole up by that mechanism to arbitrarily close to 1. And then you get into the grubby astrophysics of magnetic fields and everything else that would act as a drag to reduce that spin. So people have done simulations, MHD simulations, that suggest about 0.8. And there have been at least two observational papers in the past couple of weeks. One of them was for an X-ray source in our galaxy looking at iron lines and claiming to get a value of about 0.86 for a spinning black hole, and a supermassive black hole in a galaxy, and I've forgotten how they did it, but claiming to get 0.99. So astrophysically, it's still all over the place, and it's not clear what the accuracy of the astrophysics, the observations is. But it's very interesting if there's an upper limit on what you can get by this method. But nonetheless, this is an upper limit on equal masses. If they're unequal masses, then it's more like dropping a single grain of sand into a spinning black hole. If I drop a lot of them in, I can spin that up.
Just to add a little bit to that, those MHD simulations are only appropriate in very specific, may in fact only be appropriate. They may not be appropriate at all, but only appropriate in very specific class of systems.
Oh, yeah.
Hydrodynamic thin disk simulations show you can get up much closer to 1. And then the other thing is that there are a number of the iron line measurements people can argue about, but there are a number of other kinds of measurements that people can do in trying to fit this spectrum. And they get spins that are also a little bit all over the map. Things like two I know of, and I know there are at least 3, so I'm missing one. There's 0.7 and one's consistent with unity
Yeah.
It's consistent with unity, presumably closer to the plus or minus 0.1, or plus or minus 1. So.
1 plus or minus, yeah. So, you know, in talking to Mike and Latham this morning, things have been raised. Being theorists, we're liable to go back off and start looking at some analytical property of this, like what happens if you add spin, or as they were suggesting, that we try modifying the way we set up the data, just so to verify my conjecture, which is, that's a conjecture I'll stand by. The other one I don't know about. Which is that, you know, it doesn't matter whether you set them off like this or whether you set them off like this. You know, it's part of the same orbit. You should get the same kinds of behavior.
Is all this funny behavior, is it just spin orbit coupling?
No, actually, there's very little spin-orbit coupling. We look at the spins of the black holes as they evolve. And the cleanest case would be to look at, say, one of those. And if you look at the spins of the black holes, these are non-spinning to start with. They go flying by, and afterwards they get a spin of 10 to the minus 3. So, no, there isn't a lot of spin-orbit coupling. Which leads to another possibility. I won't call it conjecture, but it is that really what happens is that you don't have any spin-orbit coupling until you get what amounts to a highly distorted and rotating black hole. The limit on the spin of a black hole is on a stationary black hole. And I said effectively, I'm not sure whether it actually is a black hole or not. We're getting the horizon trackers out to try to find out exactly when the horizons form, when it actually forms that final black hole, and find out what part of these things are radiated prior to that and what part is radiated afterwards.
Well, if there are no more questions,
Thank you.